Welcome back. Hopefully you got some rest before your March Madness bracket was totally destroyed. Yeah, that was a rough loss. I mean, it was a really good game, but that was tough. Really? Oh man, heartless. It did work, yeah, but still. Do you remember where we are? What class this is? Coming back to Applied Mechanics number 2. What are we up to here? Thinking about it? We did 4-bar linkage, yep. Yeah, so we closed out module 2 of like thinking about dynamic motion in module 2, and now we're into like constrained equations of motion. So one of the reasons I do module 2, like a lot of times it's kind of tagged on at the end of a dynamics class, but 75% of dynamics engineering is module 2. It's just like, what is the geometry of motion? Like, how do I define how fast things are moving relative to each other? So that's why I want to do it like right up front, and then we can move on. Now, this is like the other 25%, or like another like 15%, and then there's some other stuff. But if you're doing dynamics as a profession, most of the time people just want to know like, if you're connecting parts to each other, how do they connect and what are the constraints on their motion? And then the next step after that is like, okay, now, like what's the natural frequency? How much, like is this stable? Is it unstable? Like all the next stuff comes after that. So anyway, now we're here looking at free body diagrams again and thinking about what are the equations of motion. So if we have a degree of freedom, how do we write like these are how acceleration and position and velocity are all related. And to get there, we started off with some more vectors. Can't spell victory without vector. We were looking at like rotating systems, but we'll try this again today because looking at homework, or now we're on to, or wait, did we get to 3.2? No, we didn't. We called it a day, right? I think that was a good choice. So now we're at 3.2, which is kind of a statics problem. But now that we're in dynamics, the sum of the forces equals 0 doesn't mean that it's standing still. It just means that it's not accelerating. And that's fine. So we have 3 forces that are acting on this point, on a particle, but on some point. If the resultant is 0, where is force number 2 pointing? That's the main, so it's asking what is theta, but really it's saying like, we know the magnitude, it's 10 newtons. Where is that 10 newtons pointing? how do we stop it from moving? So I want to know, like, take a look at this problem. I want to know how you would start this rather than jumping into, like, here are the steps that you should take. So let's try that. And it's a good refresher. Cut our teeth again. Okay, yeah. Just sum of x and y. E value. So E would be like a unit vector, say like EX is pointing one way, EY is pointing another way. Like, yeah, or I and J. Or, yeah. Yeah, good like refresher kind of question is like if we have an EX and EY, it doesn't have to be horizontal and vertical, but most of the time that's the way we think about it. But if you're trying to be obtuse, you can always say that it's like all cockeyed, depending on what you want to do. But, so we know like what those components are. Writing down vectors. Yeah. Sum up the EX and Y.
Yeah, and then individually they each have to be 0, right?
They both have to be 0. Yeah. Okay, that way you can define the angle to start wherever you want. As long as it's consistent with equation. Yeah.
Oh, I got two answers. You got two answers? Yeah. I don't know what to do with that now. Yeah.
So you solve
You have the X and Y components. Yeah. All right. So I saw some people jump right into free body diagram, which was like, yes, nice. Or some people are like, no, I can math my way through this. Professor Cooper and his diagrams are all, that's for lunatics. So we can try to math our way through it, right? So we could say F1 plus F2 plus F3 is all equal to 0. So if everything's equal to 0, it's not accelerating, not that it's not moving, but it is, but it's not accelerating, then my x components have to be equal to 0, which is 2 plus 10 cosine theta, and then no x in the F3. And all my y components are 0. So that's a -5, +10 sine theta, +5 minus 4 root 6. I don't love that, like 5 minus 4 root 6, but you know, it's okay. It's fine. We do like do a -5 plus a 5, so some of it works out. So now I've got two equations, right? For one unknown, cosine theta is a -1/5. And sine theta is 2 root 6 over 5. Like that. Okay. So we're done, right? Just two equations, one unknown. Or we could divide them and say like tan theta is something. So what angles, what did we solve for? What angles have we found? Try it out. Oh, yeah.
For cosine, theta is like 101.5.
Okay.
And then for sine, it is 78.4.
So 101 versus 78. Are they both the same? It's the same answer? It's different directions, right? And I think depending on how you set it up, sometimes -78 comes in there, depending on how you solved it. So which one's right? 101 or 78? They both solve the problem, right? At least the math, in terms of the math that we need to solve the problem. But which one solves the engineering problem of like, we don't want this thing, we want the sum of the forces to be 0, we don't want acceleration. You can always guess, I guess. I don't know. Wild guess. So let's back up. What does the free body diagram look like? I know, oh yeah.
I plugged in 101.5 into the top equation.
Yeah.
And I got something that was close to 0, as opposed to when I plugged in 78.4.
Okay. Yeah.
So I'm assuming that's right.
Maybe, yeah, assuming. Where are these vectors pointing? Try this. Like, what is F1, F2, just like roughly, like what are they pointing in different quadrants? Like what's going on? Where are these things pointing? Because if we know like where F3 and F1 are pointing, F2 should be the opposite of like kind of their sum, right? So it's got to be pointing away from those. Yeah. Like 4. Okay. Yeah. So F1 is down 5 and over 2. Okay. What about F3? Where's that one pointing? I know 5 minus 4 root 6, but 4 root 6 is more than 5. Down, straight down. Like that. Cool. So now F2, we know roughly it has to point up and away from, like, not quite opposite F1, but like F1 kind of that way a little bit. So it's got to look something like this, right? Where's my angle theta? Take a second and try to draw what theta looks like in this diagram. Where are you going to put theta? Because really you're defining, like, if theta is 0, where is F2 pointing? That's the question that we want to figure out. Horizontal. Yeah. Okay. I guess that makes sense. Then 101. Yeah. Okay. That makes sense. Yeah.
Would it be that 101 is measured from this side and then this side?
Yeah.
So I mean, it's
Same. Yeah.
because this negative 70 would come from.
Yeah. Yeah. It just depends on what you want to use.
All right. Yeah, you're also making the left side.
Yeah, because then a positive angle is clockwise. Okay. I drew it up there because my thought was that if I have two forces pointing that way, I need one force pointing this way.
Okay.
Yeah, because like if I add those two forces together along this line.
Oh, that makes sense. Okay.
Yeah, because like this plus that is pointing somewhere.
Yeah, it doesn't make, yeah, okay.
All right.
No, because I was like, oh, okay, I can just put unit vectors, so I
Yep.
would assume.
Yeah, no, that makes sense. And really what you're doing is saying, like, this is angle theta. So you solve for theta into the way of theta.
So basically, this is still right, technically.
It's still right, as long as you say that this is theta and then theta is.
So then this would be my theta.
Yeah.
If I, okay, and then this would be my other theta. Or like if I did.
Yeah.
Okay, that makes sense. All right, and then now we're answering the question, would it be this or this?
Yeah.
Well, I mean, I think this is.
Yeah.
Yeah.
More than 90, right? If it's
Oh,
less than
yeah.
90, then the whole thing is that.
Yeah.
You can make them all up.
Yeah, like a costume. I'm hoping to get my lab.
Based on the equation that I have that we All right, so based on the information that I've drawn up here, this is, I would say that this is my F2, and that's my angle theta. Because I said EX is pointing to the right, so when theta is 0, cosine theta is 1, sine theta is 0, so then F2 would be 10 newtons along that x-axis. And then as I increase theta, I start moving away from the x-axis up to the 90. Now I'm on the y-axis, and then more than 90, I'm pointing quadrant 2. So if this is my diagram, like this is how I'm defining F1, 2, 3 and my angle theta, then it's got to be that 101.5. Otherwise, sum of the forces is not 0. Like it's not pointing opposite. What would EX and EY look like in this case? Where would they be pointing? Is it just wrong? Like there's no possible way to put theta over there? What does it do to our like EX and EY unit vectors? Yeah.
But maybe like reverse the EX direction.
Yeah. So EY would still be pointing in the same direction, but EX is now saying that it's pointing that way. But it's also kind of messing with our, it would mess with F1 too, though. We would just, yeah, this would get a little, this would get very confusing because now F1 technically should be over here, right? Based on how I drew it, which means F2 should be over there. But anyway, so if I'm taking like theta off of that opposite angle to say that yes, it is 78.5, then really I'm giving F2 its own coordinate system pointing in the opposite direction. So this one is possible, just very confusing. My suggestion is always like use the x-axis as your zero angle. There are cases where you don't have to do that, but for the most part, it helps to just say zero angle is x-axis. So it's confusing. It's technically not wrong, but a little confusing. Anyway. Bless you. All right, I said we'd practice this again, same as like problem 3.1. And so we're doing all this vector analysis because we're gonna use vectors to create equations of motion. And because it's constrained, like sometimes our coordinate systems will be moving with the parts that we're talking about. So being able to go from one system to another is a good skill so that we can actually define equations of motion and get it in terms of like scalar values out of vector equations. Okay, so what are we actually being asked for? We have kind of 4 coordinate frames, or like 2 main rotated frames. One is system I. Another one, system A. They're both offset by like 30 degrees, one to the other. We want to define the Cartesian coordinates for I, Cartesian for A, and then polar coordinates for I and A. What's the difference between polar and Cartesian? What are those things? What are we talking about?
Cartesian would be like x and y.
Okay.
And then polar is the one where it's like theta for the angle. And then,
Okay.
And then I think r for like the
Yeah.
distance from the origin.
Yeah, so polar is just describing distance and direction, like where is the thing and how far away is it from the origin. Meanwhile, Cartesian is splitting it up into those x and y kind of coordinate system. All right, so I think we know what we're doing. So I want to say this is RP. First step is just like, what is this vector? What are we dealing with? Where is it? So just using the E1 and E2 components. So coordinate system I, oh yeah. And highlight it. So in I, what are those two components?
So just be 2.3.
Yeah. It's just right there. Yeah. There's no math. That's what I've seen so far. Any speak now, forever, hold peace. Seems good. Take the distance along the x, distance along the y. Those are our x and y components. Cool. Nice when things are just sort of laid out there for you. So now I want to find what are the components in that rotated Atlanta frame. Like Atlanta, sort of. Where is it? Is the x component bigger, smaller, y component bigger, smaller? Like what happens here? And this is like the last thing we did before spring break. So I want to know like what you're thinking about it, and then we'll step through one of many there's lots of different ways to get there, but we can think about it however you want to go through it. How do we do that part? X is bigger. Yeah, because we're getting like closer to, like the limit would be like if the x component is the magnitude. Yeah, nice. Yeah.
It's like the angle, like the additional angles.
Okay.
That adjust it based on, the adjustment of the
And then since the magnitude is the same, you can use that as the hypotenuse or
Yep. Yeah, you can do that.
and
then
I
say
like to know.
Yeah, r cosine is r.
And then the polar coordinate. You can actually just get the angle.
Yeah.
Since the magnitude is the same, it's whatever.
Yeah, makes sense. Two triangles. Triangles and triangles.
Yeah. I'm referring to like last week or the week before.
Yeah. Yeah. Okay. Are you thinking of it as like finding new unit vectors or tree?
No, so what I did was I found the angle, but there was no angle from the original coordinates. So I just found the angle from 0 to t there. And I subtracted those from there.
All right, so there's more than one way to go about this because it's a geometry problem. So you can do you can draw like different triangles on there and try to find like different sides of the triangles in that way, or we can look at like unit vectors and think about if we rotate a unit vector, how do we define that in the original coordinate system? So like this is, oh, sorry, this is E1, this is E2, and then we'll take this one, rotate by 30 degrees, and now we have A1, A2. So if this one's 30, this one's 30, and my new like A1 vector, I can write it in terms of E vector. I can do back and forth. Like if I know E1 and E2, I can write A1 and A2. So what do we want to do? We want E1 in terms of A1 and A2. Because then I could plug it into my first I vector equation. I can plug in E1 as A1 and A2, and now I no longer have E's in there, it's all A's. And then I can do the same thing for like E2 is something A1 plus something A2. Does this look like a promising approach, or is this like, what the hell are you talking about, man? I'm just trying to draw some triangles here. Or there's always like rotation matrices if that's your jam. No? No response. Yeah.
I don't know if this is sort of like just a very similar approach to doing the same thing. I sort of just found the original angle from like the 0 angle to our desired vector and subtracted 30 from it.
Okay. Yeah. Yeah, so I think that one would be kind of like right now we have, if I call this angle, call it alpha, like that's my like defining something like that, like this in Cartesian I, it's alpha, Cartesian A, now it's alpha minus 30. So now this is going to be R cosine like that. So find hypotenuse, go for it that way. Something like that. It will, so you'll end up with the same result. Yep. I like unit vectors because then I can always find like same equation to convert any vector into, rather than dealing with like each vector as like its own trig problem. I can have like a general, this is how I get from one system to another, but however, it works. Do you know what those would look like the A1 and A2 components for E1? Or not interested? Come to it some other time. Yeah.
The A2 won't be negative since it's like going below the A1. Like,
Yeah, so we move like in order to get, so we're saying E1 is like something along that A1 and then negative something along that A2. So like a negative sine 30 and a positive cosine, kind of like that. And it's always sine and cosine for as you're flipping from one to the other. Then we got sine 30, cosine 30. So either way, like whether you want to take these values and plug them into that first equation, or you want to solve for hypotenuse and then do the angle, hypotenuse and angles, like either way, same result. You can try it however you want to go about it. Are we at time? We're at time. All right. So we'll pick up next time. Thanks a lot. Welcome back.